Look at this beautiful image taken by James Webb's MIRI or mid-infrared instrument. Doesn't it look amazing? Well, this is a supernova remnant Cassiopeia A located about 11,000 light years away from us. This supernova was first observed at about 1572 by Tycho Brahe, which means that during about that time the light from the supernova actually arrived at Earth. Since this is about 11,000 light years away, the supernova probably went off 11,000 years before. The big shell of gas that you see in this image has actually been expanded for the last 11,000 years at about 4,000 to 6,000 kilometers per second, which is super fast. So imagine how big the shell of gas actually is. It's pretty hard to get an idea of how big the structure is unless I give you a little bit of reference. So for your understanding, the scale of this supernova structure at this point is about 13 light years across. And for comparison, the size of our solar system is just 0.000127 light years. So this structure that you see is about 10,000 times larger than the size of our own solar system. So this is actually a massive structure that we are seeing out here. This particular supernova remnant is actually really bright, not only in the optical wavelengths, which has been observed by Hubble, but it's also super bright in radio, mid-infrared, and also in the X-ray. So usually super energetic events like supernova explosion, since they carry so much of energy, they are usually bright all throughout the electromagnetic spectrum. And this is quite cool because this allows us to use the different wavelengths of telescopes across the globe to observe one particular phenomenon. And this is actually something called multi-messenger astronomy, which means you are actually observing a source using various wavelengths of light. I have always been saying different wavelengths of light corresponds to different energies and different physical processes going on within a particular system. We have quite a wealth of information when it comes to supernova explosions like this one. I mean, this picture as it is breathtaking, and this has been actually taken by multiple filters, the MIRI instrument. So just to give you a perspective, let's take a look at the image over here. So it says it uses MIRI filters from 5.6 microns up to 25.5 microns. So if the 5.6 microns has been color coded by the blue color, and the 25 micron has been coded by red colors. So what it's trying to say is the lower wavelengths of light corresponds to a much higher frequency, therefore a much higher energetic phenomenon. So it's pretty much the same logic with visible wavelengths, but this time it has been replicated in the infrared wavelength as well. So typically people use blue colors for lower wavelength infrared light and red colors for a slightly higher wavelength of mid-infrared light. By taking a look at this image, the bright orange shocks that you're seeing outside is basically gas that is moving at extremely high velocities of up to 6,000 kilometers per second. And as this sort of rams into the surrounding pressure, it creates this shock wave kind of structure and forms this interesting knots that you see here. Particularly in the remnant's exterior, if you notice properly, at the top and the left, you can see a material which is appearing orange and red. And this is due to the emission from the warm dust. This is basically where the ejected materials from the exploded star is, as I said, ramming into the surrounding circumstellar material and thus glowing bright in this particular orange and red color. Now if you notice at the interior to this outer shell is where you will see all the filament-like structures, and they are in actually bright pink colors with clumps and knots. This basically represents material from the star itself, and it's likely shining due to a mixture of various heavy elements as well as dust emissions. And the stellar material can be seen as fainter wisps near the cavity's interior. Another interesting feature to note is a loop represented in green which extends across the right side of the central gravity. Its shape and complexity is sort of unexpected, and this is why observations like this are so much interesting to study. All of this phenomenon are because of the crazy gas dynamics and the crazy energies given off by supernova remnants. This particular supernova remnant has also been observed by Chandra first, the late 1990s when it was first launched. And during its course of time, Chandra has allocated several hundreds of hours observing this particular supernova. Because as I said, supernovas, being extremely energetic events, are very bright in X-rays. And allocating a lot of time to observe something which is so bright in X-rays can give you a wealth of information. Chandra has actually discovered multiple elements which glow bright in X-ray on this particular supernova remnant. So this is a composite image in X-ray which has been taken by Chandra. Now we see the different elements that Chandra observes. The first is silicon, which glows bright in red. Then you have sulfur, calcium, iron, and finally, this is the composite of all of those images together. These supernova explosions can give up to energies of 10 to the power 40 ergs. Now that is a ton of energy. Therefore, it accelerates and pushes away gas at velocities of up to 6,000 kilometers per second when it first explodes. Now that is 6,000 times faster than a bullet. So these are super fast gas that is accelerating outwards from the central core that has now exploded. And since we have a rough estimate of the velocities of the shock front, also we have quite a bit of good idea about the densities of such environments, we can actually go ahead and calculate the mass of this particular elements that were given off in the supernova explosions. So by looking into the Chandra data, there has been an expulsion of about 10,000 Earth masses of sulfur alone from this supernova remnant, and about 20,000 Earth masses of silicon. Finally, the iron in this particular explosion weighs about 70,000 Earth masses. And when it comes to oxygen, there is an estimate of 1 million times the Earth's mass of oxygen that has been found in this entire supernova remnant. From all of this, what you can understand is supernova remnants are super rich in a lot of elements that we are essentially made out of. So all of these heavier elements in the universe actually gets forged inside of a star. And a way a star achieves this is basically with a ton of pressure. So what happens in the core of a star is nuclear fusion. Two hydrogen atoms fuse together, forming helium, which gives out a lot of heat and light. And this nuclear pressure is what holds a star against its gravitational collapse. So after a point of time, when all of the hydrogen is over and there is no more hydrogen to fuse into to form helium, this nuclear pressure slowly falls down. This causes the gravity of the star to overcome that nuclear pressure and fall inwards. Now what happens is the star sort of is starting to fall inwards. A lot of the helium that had been already formed inside the core of the star now fuses in between themselves and starts forming heavier and heavier elements. And this process of fusion actually again reignites the star's core, slowing down the process of that infall. And this continues on and on and on, and you form elements like carbon, nitrogen, oxygen, silicon, so on and so forth, until when you reach iron. Now basically iron gets forged in the very innermost core of the star. In order to form more heavier elements, now this process requires energy rather than giving back energy. So as a result, the gravitational collapse finally wins, and the entire layer of the sun sort of collapses onto the iron core, sending a huge shock wave outside, which is what is basically supernova. And this shock wave sort of explodes away all of the outer layers, enriching the surrounding with all of this element that was once forged within the star. Basically, stars which are 8 to 10 times heavier than the mass of our sun will end up in a supernova like this. Stars which are less than 8 times the mass of our sun will basically form a planetary nebula. What is a planetary nebula? Rather than forming a big explosion like supernova, the star goes into a red giant phase, throws out its outer layer into its surroundings, spewing materials which had once formed inside the stars and enriching the surrounding with again all of the heavier elements that it formed within. And planetary nebulas are some of the most beautiful looking objects in the universe, as you can see in all of these pictures. Depending on the size of the star, it will either go supernova like CAS A has, or will form a beautiful planetary nebula. Now, if stars are more massive, which a lot of stars are, they form into white dwarfs, and even if they're more massive, they will probably collapse into a black hole. So not all stars have the same fate when they die. depending on their mass, they have different outcomes. Nonetheless, this particular image of CAS A is really beautiful. I'm sure this latest observation by James Webb will give us astronomers a lot of more in-depth about the complex dynamics of gas flows that are actually going within this particular system. I'll keep this video really short and try to end it over here. But in case you guys like this quick cover of CAS A, please subscribe my channel and leave that like button. And in case you want to know more about planetary nebulas or supernovas, feel free to leave that in the comments, and I'll catch you guys in the next one really soon. Thanks.